Okay, so today we're going to talk about feature engineering and feature transformation, feature selection, and how to using these part and how to use programs to and actually implement this. So we're going to using bunch of examples to illustrate that, but we have using those concepts to demonstrate that this is very important. Otherwise you are getting like garbage in, garbage out, and you have to process and clean those data properly. So there are three things that we have talked about, and definitely and the feature transformation, feature selections, and also the most important part is feature engineering. So and we will emphasize the feature and engineering, and we will and trying to see how we can transform into and those raw data into features that is suitable for modeling. Feature transformations. So this is and transform the data to improve the accuracies. Feature selections. Say we have a lot of features. We are not using all the feature. We're just using some partial features. So this is something that is very commonly will be used. In fact, in this and the data that we have encountered, we have like 1800 features. That's a lot of features. We need to just using part of this. So in this whole notebook, we're going to demonstrate with a code. So I mean, last video we demonstrate everything with concepts, but this we will demonstrate this with a code. All right, so and we're going to using this and the competitions. So this competitions data set, I think that's a part of the data set. So this data set is from 2 Sigma Connect rental listing inquiry, like Kaggle competitions. You can click that. It actually linked to Kaggle competitions, and Kaggle is a website that they will launch a bunch of like data science competitions that you can practice all your data science and the machine learning skill sets on those realistic data set. So it is very important that you should try those in the competitions by yourself to polish your skill sets. So it's very important because and if you want to enrich your resume, and this is a golden opportunities to try that out. And also right here, we're going to using this training data set and trying to do some feature engineering and feature and a selection with that. And this is, we are loading all these like necessary libraries. We're going to load the data. This data is actually in this Google Drive. If we look this data set, we will see this has 15 features. All right, so this is, I mean, the number of the, and the column is only 15. The last one, that is interest level is a target. So there are three possible target values that we can choose, and we can predict as one is low, one is medium, one is high. So this is actually give you whether this new rental listing is popular or not. So this is your task. And also, and to evaluate, I mean, the solutions, we're going to using the log loss. I mean, the smaller, the better. So you can using these kind of like things. You can click through. You can and create a Kaggle an account. You can download this and data and participate those competitions. So here we are just using this data as like one examples to demonstrate these feature engineering and feature selections. Okay, so we can see this actually has a lot of features. For example, this features including the bathroom, bedroom, building ID. I mean, this is like fairly random. This is like time and created, and this is descriptions. So you can see this actually descriptions evolve a lot of and the word sentences to describe, and the same with the features, all these kind of things. Possibly you can using the natural language processing to actually to demonstrate and to help us to classify whether it's popular or not, and so on. There are a lot of things and a lot of interesting things, and as a features. So this is our target that we want to predict, which is our interest levels. It has a low, has a median, has high. So in total, it has a lot of data, almost 50,000 entries. For this descriptions, you can see it's actually very and a lot of word. You can see this is a description. For example, I want to see the first one. Oh shoot. I can't do this way. So dot loc. I forgot how to actually do this. Is it this way? Oh no. All right. So basically, this is so if you look this like so descriptions. It actually give you the descriptions for each of the data. It give you, for example, the first one that's like spacious, 1 bedroom, 1 bathroom, and so on. And you can see these are the descriptions for that specific data entries. So we can take advantage of this if needed. Okay, so we can using the df.info to actually find out those informations. You will see these bedroom, they are like float, integer, and the time, and which is date time in second right here. And also you have a like object feature. They are all like strings. That means actually using this object. So the data type is actually the object. All right. So and here and price is the integers, and interest level is object as well. So you can see we have a lot of data types. For example, date time has one of the features. Float is 3, integers 3. The other 8 are objects. So and the first things is very important is we need to to extract features. So we want to take advantage of these features and other features as much as possible. For example, these descriptions for those rental home may have a lot of like rich information, but we need to extract this out. So how to extract this like informations and how to extract the informations from the texts. And we have a talk about this, and we can tokenize those and the sentences. And after tokenizes, and we are going to build a model on that. So here is the way that we have a talk about this. One is tokenize, that you can split those texts into like words, and which is in some senses as the tokens here. But it's basically, but we cannot split, and sometimes we cannot split the word like completely. For example, Santa Barbara is considered to be 1 token, but not 2. But rock and roll should be, and it should not be split into 2 tokens, and so on. So there are certain rules that we can follow. There's the building package actually to help us to split those kind of sentences into the tokens. So that's why there are it's already ready to use tokenized methods to take into account of this peculiar part of the message and of the language as well. So after tokenize, we're going to normalize the data. So we can do some like stemming or like lamelizations. So what is that? Meaning we have to talk about this in a part of, for example, he or him are the same thing, and are going to map into the same tokens. There are like a similar process to process this form of word. So there are a bunch of differences. You can click this link to see the differences and how to normalize this data. All right, so here we're trying to using the simplest possible ways to model the word. That means we're just trying to treat as an order document as a sequence of word, and we're going to represent a simple and vectors. So the first, the simplest possible way is just we using backward words. That means we don't care about the order of the and the sentences. We only count the frequency of the words. So that means we create a vectors of the length of the vocabulary. I mean, that could be super long, and compute the number of the occurrence of each word in the text. So that means I don't care about the order, how this like word shows up in this text. I mean, what I only care is the frequencies of those words. And I'm going to place like that number of the occurrences in the right positions of the vector. So you and see a gigantic vectors. For example, here we have these three sentences. I have a cat, you have a dog, you and I have a cat and a dog. So that means I'm going to create the vocabulary. So, and this is my dictionary if we are trying to build a vocabulary like and directly. That will be 0 is and 1 is dog, and 2 is have, 3 is I, and so on. So basically, and this is my mini dictionary, and it's basically a mapping from the index into word. Then for each sentences, I'm going to do this kind of mappings. So basically, I have a cat is basically, I'm saying I shows up once, a have shows up once, a shows up once, cat shows up once. So that means we have actually has created vectors that has 4 ones in this vocabularies. And on the last one, we have a you and I have a cat and a dog. So a and actually shows up twice, and shows up twice. You shows up once, have shows up once, cat shows up once, dog shows up once. So that's why you actually will have the vocabulary like that the and actually shows up twice, and also a and actually shows it twice. So this actually using these kind of like and the number of the occurrence of these words and it shows up, and we just summarize in this simple vectors. But of course, this vocabulary or the dictionary is super small because we only have this 7 words that we have. But in reality, what we are trying to do is, for example, this is how you get ends. So you're going to tokenize that and build the vocabulary over all the documents. So that means that will be the whole list of vocabulary. That could be like 50,000 possible words, right? So this is very common. Think about your dictionary. So I'm going to build a like vocabulary and over all the documents that I'm going to encode these sentences by using sparse vector encoding. That means I mean, technically, this is actually like could be like 50,000, like and the size of 50,000 and the vectors. But most of like entries is, I mean, actually 0. Only there's like bunch of like entries here that shows up. This is how you get ends. These like entries is actually 1. So this is a very naive way to like and to like encoding those sentences. And also, in practice, you need to consider stop words and the maximum length of the vocabulary and then like more efficient way to and on the like data structures. So that means you are not going to convert this into this gigantic vector. You actually need to convert this into a sparse vectors. So take advantage of sparsities. Actually can help us to go through things quickly. So they are like, and of course, like if we're using this kind of like algorithm, we are basically losing the orders of the word in text. For example, I have no cows, or no, I have cows, and it has like identical after we do this like backwards vectorization. But of course, it has completely opposite meanings. So what we can do right here is, I mean, to avoid these things, we can do is we can using the engramming, I mean, instead. So that means, I mean, instead of we using like one word as one token, I'm going to consider as a pair. For example, right here, I'm going to consider this is whole and right here as a pair as one token. So I think about this right here. We have this is how you get ants. So this is we think everything as a pair of nearby words. So this is something called a sequence of two consecutive tokens. So this will be n-grams. I mean, this case is we're considering 2 grams. And of course, we can make it like more complicated, and it could be like 3 grams and 4 grams and so on. So right here, we can using this count vectorize actually do this process for you. So that means, for example, now I have cows and I have no cows. If you do this fit transform for that for n-gram, that means if n-gram n equal to 1, this is turning into backward words because we only consider one token as one thing that we are ending the sequences. Now you can see, no, I have cows and I have no cows actually have exact the same like vector representations, but of course they have a different and opposite meanings. And you can using this to actually do this vocabulary, then we can see, okay, so we have only have like 4 of that. We have no, we have I, we have and cows. And this like, and these 2 sentences is kind of like reshuffle of this like 2 of this. And of course, we can do more complicated. For example, I'm not going to, I'm going to work more than like just, and back of words, I can do 2 grams. So that means 2 grams is I'm going to, so like n range from like 1 and 2, that means I'm going to consider like, and back of words, and also I'm going to consider 2 gram at the same times, both. So that means, and not only we are trying to, I mean, think about this way. So we are thinking about as a pair. So here we will have no I. I mean, as a pair, I have is 1. I mean, it's another one. Have cows, it's another one. And I have no, and no cows. They are all pairs. So if we do this, actually the vocabulary becomes like that. They will be more complicated. Here, in fact, we have and actually 9 and 9 different and tokens. And you can see these like nearby, like 2 tokens together becomes like 2 grams. This will be and our new type of tokens, right? So this actually consider much more and information. So this is basically we consider the relation and the like effect of the previous words. So that means we have certain memories of the previous words. So basically it says no I have cows, have no cows, all these kind of things. Okay, so this actually being your vocabulary. So if we consider 2 grams, then these 2 sentences were like identical in backward words, in fact has a different representation in terms of vectors with 1 gram and 2 grams at the same time. So you can see these 2 actually give you 2 different end representations. Okay. And of course we can, I mean, generate any like gram of characters we want. Sometimes that's also possible. And this approach, it's we can account for the similarity of the words or handle typos if needed. For example, a word or words are like kind of the similar words, and with that we can actually handle all these kind of information. And also this will be helpful with the typos here. So for example, right here, so we can do these like 4 different words. I mean, this is basically, I'm considering 3 gram, but we are only interested with the characters, not the word. So like one and one token will be just like one character, but we're considered as 3 gram. So that means I'm going to consider a pair of like and a triplet of the characters, like triplet of the characters. So what I'm going to do is once we do this like fit transform, you will see right here, we're actually to see these triplets, right? So we have seen and all these triplets of the and the the word. So we are the one token is no longer being a word. In fact, it's one token being one character, and we are only considering with 3 characters. The reason that we have like one space here because in the beginning, because we consider this WB, and what is the WB means that means at the front of each word we were going to consider there's a space in front of that. And we are going to consider at the end of this word, there will be also a space, consider that. So that means we will have that kind of situation that is the space AN or like EN space, all these kind of things, right? So this is give you some idea to indicate this is the end of this word. That, the word should stop right here. Okay, so and you can see this is the vectorization of the first word of Anderson. This is the vectorization of the word of Peterson. And you can see they have some similarity here, right? Like an Anderson and Peterson is kind of similar because they all ending with ERSEN. But of course, they should be different from like Smith and Peterson and Petrov is kind of like closed state because they all start with the PET. So you would like, hopefully you would feel like Peterson and Petrov are kind of close together if we want to like vectorize everything. And also Anderson and Peterson should be close to each other because they like sounds quite similar in terms of characters. So we can calculate the Euclidean of like N1 to N2, N2 to N3, and N3 to N4. Like hypothetically, we will assume this N2 to N3 to N4 is like largest. As you can see right here, this is quite fit to our intuitions. N1 to N2, the Euclidean distance is 2.82. This one is 3.16, and this one is 3.32. So obviously the distance is largest for this one. All right, so and also there are a bunch of things that that we can do, and also for example, and we can add in more and informations into the back of words. For example, some words are really found in the corpus. That means in the document. That means it's particularly important. And for example, right here, maybe cows is more important because that's the word and it shows up not regularly in the document. However, no or I or a, all these words is commonly used in all documents. So these like words may not have the important informations as the cows. So and basically, if we want to emphasize and give the weight for each characters, I would like to prefer to give higher weight for those cows, right? Because it actually has some like important meanings. Could have like important meanings right here. All right, so so this is the idea of TF-IDF, right? So basically, it makes sense to increase those weight of those like more domain specific words to separate them out from common words because all these words is like shows up everywhere, usually doesn't carry a lot of meanings. But those cows or like teachers, all these kind of things, and actually shows less frequent. It might give you more informations to those words. So this is called TF-IDF. It's called term frequency. inverse document frequencies. It's more complicated, but you can just click this references wikis. You can see how they actually process that. You only need to know this is a very important, and also the way is, and the difference is, and between TF-IDF and the bag of words is actually TF-IDF is going to assign the weight to each of word, right? So this actually gives you some idea. And also, like another way is what we can do is we can do like word to vector. So basically, we're going to change and map like any word to actually and a gigantic and a vectors, and then we can process this word with like additions, subtractions, and inner product, all these kind of things. So this is kind of like word embedding algorithms, and using this kind of method, like you can like actually vectorize this word in like very high dimensional spaces, and typically that will be in couple hundreds like dimensions, and you can actually compare this like semantic like similarities. One way to think about this is king plus man minus woman, and you should think about this as being the queen. So that means if this vector here is a man, this vector is a woman. This is like this direction always like it's more like feminine and a feminine. So that means you have like say if you want this process being like king minus woman plus and king minus man plus woman, it actually will output a vector that is very close to queen. Okay, so this is basically very classical examples of these operations of the concepts of vectorize of the word. So if we can like vectorize these kind of word, that we can use in like semantic like similarity to compare and these vectors. You can do all these kind of like and the subtractions and like and additions for those vectors. But I want to emphasize these like things are just and this model is not like trying to comprehend the meaning of the word, but just simply try to position the vectors that those words used in common contexts that kind of like close to each other's. It doesn't mean that you always will have like say this kind of like nice result. Sometimes you will have, sometimes you don't have. But a way of thinking is we're trying to cluster those words that has similar meanings together. It's more like clusterings that we're trying to use. So there will be a lot of like very interesting like and examples will come up. And of course, this kind of like word to vector will be trained on a very large data set in order to fully understand of the vector coordinate to capture this semantics. But usually what we do is these kind of pre-trained model, and we are not training all these kind of word to vectors by ourselves. What we usually do is so what we usually do is we just taking this pre-trained model of our like own task. You can just download that and we can just use that. We never actually train this word to vectors by ourselves. Okay, so usually don't. Okay, so this is text. And obviously text is very important. And another one that that we and they use a lot is images. So we have a talk about that in the last video that and a lot of people actually and in the past they use like and the like traditional ways to come up with the features of images. However, there are a lot of things that being used in the past that we're using like deep neural networks to actually to and output and create the features for those images. And instead, for example, we can just download and you don't need to come up with the architecture, train this neural network from scratch anymore. instead, you are going to using this state-of-the-art network with the weight that we already know. Then we can just like adapt this like network and then just and output the features of those features that will be useful here. For example, this is the image of the test data set being used a lot, and which is like a raccoon. However, what we can do is we can just like and resize this thing, and we have talked about this like resizing and a lot. So you can just download this like ResNet, right? And this is all pre-trained and the network. So you can just like take it, and then later on we're going to show you, in fact, these features. And once you have these features, you can detach that and connect it to these fully connected layers of network, and you can adding one more layers. For example, to do any kind of classification problems if you need it. Then you only need to like tuning is the last layers. You never tuning like those pre-trained models. And these pre-trained models is being treated that is give you the like kind of like and the feature representation of these images to grab the important features of these images. Okay, so this is very important. And so what we usually do is, and for this image, we usually do some like downsampling, and we have talked about that in the last one. Then we just do this pre-process of the input. This pre-process of the input is basically using this like an image and a mobile net, and it's like a mobile net. You can think about it as and ResNet and using the like a mobile net to process these images. So what you're getting is and then you're going to apply the ResNet at the end to create those features and directly. Okay, so this just give you features immediately, and you can see this actual features is 7 by 7 by 2048. And we're going to talk about this in detail in the later of the courses. What does that actually mean, and how we are going to use this information to make any kind of like classification problem and prediction problems for this kind of like image and image related tasks. So this give you some idea. And for example, right here is okay. So like this is basically think about your like ResNet is something like and that kind of like feature layers. So like over there, this is kind of, you can think about a deep feature encoders to code these images into bunch of like you take out this like important features from the images, like original and a data set they are trained on the image net. They are going to create the class labelable for this image. For example, this will be output as image of the bicycles. But for example, if you want to train on a different data set, which could be a data set of like of the skin cancers, and what we're going to do is, of course, in the like image net, there's no like skin cancers. So what you're going to do is you're going to detach the last layer, which in this case is your F8. Then I'm going to connect this into another fully connected layer. It's called predictors. And this will be output the corresponding like class labels, could be like different type of skin cancers. And everything from C1 to F7 will be remains like the same to be frozen. Then you are going to using your new data just to train these predictors, right? So that will be significantly less amount of parameters need to be trained. So you can think about in the previous couple layers and these layers, they are just trying to grab the features from the images. So the way to grab the features from images will be universally to be the same, whether you are working on the bicycle like images or whether you are using the images of the skin cancers, right? So this is very important. So here, as I said, this is a classified trained on one data set. For a different one, that you just like detach the last layer and adding a new one instead. But I mean, and we shouldn't focus too much on these neural networks here, and feature generated by hand is still being very useful. I mean, this is very important. So that's why sometimes you still need to do these kind of like things. And for example, this kind of predicting the popularity of the rental listings. We may assume this bright like an apartments may attract more attentions. So you can just create features for like say average pixels of the average and the value of pixels. So this gives you some idea. Maybe we can artificially create some features to fit our like intuitions. And also another way is like any neural network cannot help to extracting the feature from meta information. For example, those images have something called an EXIF, and these have some like very important like meta informations. For example, the resolution, the camera models, or whether it used flash or not. Some even have the geographic coordinate. So this actually can give a very important informations can be used into this kind of trainings. So we actually want to take these kind of informations into our considerations. So I mean, in all data science problems, once we have images, there are a lot of ways to process images. Just to looking at this one pixels is just one of that, and there are a lot of other meta informations we can actually use that is embedded in this, these images. I'm not going to talk about this image to text. You can just look at, by yourself. This is not very popular at this point. And people was like using that like a lot in the previous ways. Okay, so this is feature engineering. In the homework, you are going to practice some of the like feature engineering techniques. I'm going to like tells you what kind of feature engineering you're going to work with, and later on in like homeworks getting more and more evolved, you will see how this is being, and you need to come up with your own feature engineerings. All right. The second part is feature transformation. Feature transformation is also one of very important things. I think we have a talk about this in the last part. So basically, what is thing is a lot of there's some methods they like to have the data is like roughly like and the Gaussian shapes. If the data is like has various like and different scales, sometimes you might have a problems. So for example, the k nearest neighbors, and if the features are not normalized, it will give you completely nonsense result. Because if think about one dimension is like located around 0, and another one it's another dimensions is on the range of couple and hundreds of thousands. That means if we try to measure the Euclidean distance with it 2 points, that the other like dimension will dominate like significantly. Then basically we getting rid of the first dimensions. So that's why if we don't like normalize those features or dimensions, the k nearest neighbors will give you garbage. And basically, so that's why the feature transformation is very important. But there are other like algorithms, for example, random forest and random boosting, all these and decision trees of that in fact has no effect to that. So that's why it's getting like more and will be like more robust because you don't need to come up with a good feature transformations. It will always work whether you transform or not. Okay, so but if you want to work on a lot of like problems that has to, I mean, evolve the feature to be and relatively the being the same, and I mean the scale of the same. So the first thing that we can think about is we can using something called standard scaling, which is the Z and the score transformations. I mean, so this is basically subtract the mean divided by the standard deviations. But and this is okay, sorry, I forgot this one. And this is basically the thing, and think about, and I mean the example that we have, I mean talk about is the task is to predict the cost of an apartment from two variables. One is the distance from like city centers, one is the number of rooms. The second one is really exceed 5. However, the distance to the city centers could be like in thousands of meters. So basically, if we want to using k nearest neighbor for these two features at the same time, without any normalization, you are basically getting rid of the number of the rooms, right? So I mean that's something that we are not going to, and and so and that's not the situation that we want to see here. Okay, so let's see something here. So for example, I'm going. So this is usually being processed like something called standard scalar. So basically, subtract mean divided by the standard deviation. Right here, I'm doing something like Shapiro and the testing. So basically, to test whether this data is actually sampled from a Gaussian distributions or not. So I mean, this data is actually like sampled from like a beta distribution. So that that we know this is not from a Gaussian. However, for sure, if we and trying to using this like Shapiro and a test, it actually give you like super tiny p-value. So that means basically says I'm going to reject the and hypothesis and then and reject the and hypothesis that is being like an Gaussians. And also, so we can do this kind of like yes and reject the null hypothesis of the like and the normality of the and the data. So basically, we can just do this kind of things as the pipelines. So we're going to do this like standard scalars. Then I'm going to do this test of the Shapiro test. So this is being and step one will be the standard scalar, and which is my Z transformation. On the second one is I'm going to apply this Shapiro test. All right, so but this and also protect and against the like outliers. So for example, and right here, this is basically, and we can do this like standard scalars to fit transformations for those data set. That we have a one outlier from like to 100. That means it's 100 is going to map into 3.15. The other one is being made and mainly concentrated as and around like minus like 0.3. So that means it's once we have an outlier, it doesn't like do super good job right here. So that's not like and I mean to some extent, it protect against and outliers. But in some senses, it's still, this outliers is still like shows up here, right? Still like it's there. All right, so the last one, yes, we also mentioned about the other scaling method, for example, minimax scalings. So this is basically we are going to scale this and the data point into the predetermined and intervals, and usually it's like between 0 and 1s, right? And all like -1 to 1. So and we can using this mini max scalar. So if we do like mini max scalar for this data, and then we know this data is it's like that. It's like we have a 100 here, right? So so you can see it's still being like and a very like close to like this. You can see the value right here is very much close to the 0, and 100 is being mapped into 1s, right? But and since we know like that, and we know the data is like, and it will be mainly concentrated at 0s, and there's 1 left at I'm at a 1. And these like two scaling and usually have similar applications. Sometimes are like interchangeable. But if the algorithm evolved the like distance between 2 points or vectors, a natural choices will be standard scaling. But like minimax scaling will be useful for visualization if we want to bring the features within the interval from 0 to 255. For example, this is, I mean, if we want to like visualize this as an images, so this will be and a way that we can do. And for example, right here, and we can do like something similar. That, and for example, this is and log normal. For the log normal and the data set, this is basically we example the normal distribution, but we take the logarithm with that. Okay, so this is, let's see, what is that? I forgot what is log normal. Okay, so okay, sorry. The log normal is the random variable whose the logarithm is normally distributed. Okay, so this is something like that. So this is obviously it's not like from Gaussians. If we take Shapiro test, it will be and reject the null hypothesis. However, if we take the logarithm, the p-value is 0.1. That means we cannot reject the null hypothesis. But this and the log normal is kind of very common if we want to work with bunch of like things. This is very close to, log normal distribution is very suitable to describe those features is strictly positive. For example, the salary, the price, the population, number of comments, all these kind of things. But to apply this procedure, usually this distribution is not necessary to be log normal, but you can take the logarithm of this data to see whether it makes sense or not. You can using this kind of Shapiro test to see whether it makes sense or not, to see whether you can reject the null hypothesis or not. All right, so there's something, and you can like think about this and read this, and particularly one very important thing is if you see your distribution have a heavy tail, that means heavy tails. That means you will see your tail of distribution spend much like longer than you expected. So this is very common if you see the salary, if you see the population, you see the ages, usually has a very and very much like heavy right tail. You might consider to take the logarithm of the data. So although they are not necessary to be perfectly log normal, but it's always a good habit to consider the logarithm of the data in these cases. So what we can do right here is, in fact, we can using another like less formal data. It's called QQ plot. Actually, if it is actually the Gaussian distribution or normal distribution, it should like a smooth diagonal line. But if it is not like normal distribution, it will be like be off. Okay, so this is the price. So this is the data set that we already have, and we know this is a price. Price is strictly positive, so it's more likely a log normal distributions. So what we do is we take the logarithm of the price. Here, what we are trying to do is we are only consider the price between 500 to 20,000. Okay, so this is the sum range because we are not going to consider anything that is very and so very extreme. So and we're gonna and so basically fill out those like prices very extreme. Okay, so if you run this whole thing and we take the like and we consider two things. One is price and another one is price log. So what we do here is we're going to create this pipeline here. The pipeline is I'm going to take this and a minimax scalar, then and of the price, and this one is I'm going to apply the standard scalars for that. So I mean this is minimax, this is z transformations. So we can do this QQ plot for that, and for the price here we're using the price. So you can see this actually doesn't look like close to be a diagonal. So that means this is not like a Gaussian distributions. So, and the same here, you can see this is not a Gaussian distribution and the normal distributions for the price at all. So we can do this with a standard scalar. This shape actually doesn't change because everything right here, whether it's a minimax scalar or standard scalar, they are all linear transformations. Basically, you subtract a constant and divide it by some constant. So this is a linear transformations. I mean, if the previous distribution is not a Gaussian, after linear transformation, it will not be Gaussian as well. So as you can see from QQ plot, this is not a diagonal plot. So basically, this is, and that indicate this is not from a Gaussian distributions and not sampled from some Gaussian distributions. However, you can do all these kind of things. I mean, just won't work. But if we do the logarithm, I mean, here we're trying to put the QQ plot of the price log instead. Right. So if we do this, it actually give you something that is very close to a diagonal now, much better than the price itself. You can see the price itself has a super like and a big curve here, but this one is significantly better. So it looks like a reasonable like and a diagonal line. So that means if we actually work with the prices right here, it might be a better idea to take the logarithm, then you apply that and put into those machine learning models, because if we directly and using prices, it will be most likely has a heavy tails. It doesn't, goes like a Gaussians. Those like machine learning models may not be like it. So a way to do these kind of feature engineering is you can take the logarithm of the prices. A lot of cases there will be like and normally distributed for those prices, and as a result, and these like machine learning models will like these kind of and will like these kind of data and the data distributions. All right, so what else? Well, I still have a lot of stuff. Okay, so let's try some like realistic data set. So we can also do, and let's come back to the data set that we have. So among these features are and also we have the number of the rooms, and also the price as well. And of course, these are two very important features, because these two features actually give that and is likely significantly contribute to whether this room is popular or not. So a simple logic will think about the cost per single room is more indicative than the total cost. So what we can do is work, and we can create a new feature. So this is very common, that we can do some like and create features altogether. So we can do the price per room. Sometimes you will see the room being zero, bedroom being zero. So that's why I'm going to apply, I made it zero that I'm going to apply into 0.5. This is like chosen more or less arbitrary, just to ensure this doesn't divide by zero. I mean, if there are very limited number of features, you can generate all possible interactions, maybe square out, cube it out, and then weed out all these unnecessary ones you are going to, and we're going to talk about later. But not all the interaction with the features will have physical meanings. And think about what is the square of the bedroom. It doesn't seem like it has any kind of physical meanings, but sometimes you can try it. And what you can do is you can using this scikit-learn pre-processing and polynomial features functions that to create all sorts of different features. But this could be quite difficult. Sometimes you don't know how to interpret that. Another thing that is in a lot of data, you have missing data, right? So this is also very important. And we can fill those missing data by infusions. So these are pretty much the straightforward way to fill out those missing data. And the first things is you are going to encode missing data with just called NA as a new categorical data if the feature is being categorials. So this is just called NA. All we can do is you can use the most probable value of the features to replace this NA values. It could be the mean or median for numerical values, or the most common value of the categorical variables. So both of that will be good, right? Or the other way, we can encode some extreme values. So for example, so you can if we do decision trees models, sometimes it allows the model to make partition between the missing and the non-missing values. What we can do is we can make this NA and the null value to be very extreme values. So and we can ensure this will not be part of the node when we do the partitions. And also, if we are working with a time series with the ordered and the data, for example, this data is being ordered as it's actually time series, and what we can do is we can take the so the adjacent values. That means it's either the next data set or the previous data set. So this is something that should work out for the time series. So something like sometimes will suggest and if you feel all the null value to be zeros or something like that, but this is not the best solutions. So if we just fill up all these value by zeros, then this it takes more time than building the models. This kind of gap fit and fillings may have create some bugs in processing and further damage the models. So that means doing this way is not a good idea. And if you feel those null values to be zero, it's just give you some artificial values and this artificial values, but during the training, the model doesn't think this is artificial values. Well, think about this is actually the true values. Then it will and give you some error data, and furthermore, it will damage the performances of the models, right? If the data is like NA, it's a null and the values, we should seriously taking care of these values, and rather than just leave it to be missing or zeros. Okay, next is the feature selections. So for example, if we have too many features, and we're going to talk about this later because if we have too many features, it might overfit, and overfitting is a very, very dangerous thing. Sometimes it might create a lot of problems. So we need to get rid of some unimportant and the features. The first one, and there are two reasons for that. The first one is, of course, the more data that we have, the higher the computational complexities. That means think about if we have 1,800 features in the house predictions and house price predictions. That will be super, super time consuming and expensive to consider all these features. But so if we just work on the toy data set, the size of data, probably is not a problem. But in the real data set, hundreds of extra features will be quite tangible. But think about the feature that we have, 1,800 features. That's way too much to be handled. It will, and that would be almost impossible to build a decision trees even on that kind of problems. A second things we're going to talk about in the possibly next videos, there will be some algorithms will take those kind of noisy data as a signals and actually overfit for those models. And overfitting could be very, very dangerous because, and you will see those training error could be very, very small. But actually, if you have a new data comes in and this model couldn't predict very well to those new data. So this is a very typical situation for the overfittings. So we're going to talk about this in detail and later on. The one way that we can do is, and obviously that we can we can remove those features whose value are not and remain unchanged. So that means it will have no information at all. So basically, if the values moves basically a straight line, so that means basically it has no information. So that means we can build. This thought is reasonable to say if the feature has a low variances, are generally worse than those with high variances. So we can consider cutting the feature with the variance below certain threshold. So this is a very common way of thinking. So for example, this right here, if we threshold of 0.7, that will have 19 features instead of 20 features. If we threshold with the 0.8, that would be cutting one more features. If we threshold with 0.9, this gives me 17 features and so on. And this is a way that it's very simple. Just we're using variance threshold. This is basically the one of the simplest way to do these kind of feature selections. Another way is this scikit-learn actually has the packages of feature selections. We can do this kind of select k-best, and also these kind of model and selection using cross-validations. We're going to talk about this cross-validation techniques a little bit later, and possibly in the next two videos. So, and this is basically we are using this kind of and so like logistic regressions to and to select this that I mean 5 best features out of it. So this is like and the logistic regressions. We can do this cross validations and with the scoring of the negative log loss. This actually give you with the mean of that, this gives you minus 0.4 right here. So we can do this k-best, which is actually better, right? See, it's and minus 0.30. So this is basically if we take the 0.9 threshold. So right here, I mean, for the k-best, actually we take the 5 best out of that, right? So we only have a 5 features instead. So here, the X data generated here, we are going and we take, I think we take the 20 features altogether. Yeah, it's like 20 features altogether. This like X data's and variance. So that means I'm taking this 7 and 17 and features. You can see this is slightly better than using the 20 features, but still worse than the top 5 best features. Right. So this is, and from here you can see this actually select k-best is doing very good job right here to find out the top 5 best features actually significantly increases scores from minus 0.4 to minus 0.3. So you can see our selected feature have actually improved the quality of the classifier. But this is, purely artificial, but a lot of cases will be useful if we have like realistic problems. All right, so that part, okay, so this is the, and also as another approach is we can using the baseline models for feature evaluation because sometimes the model will clearly show those kind of like importance of features. One of the, two possible models that we can do is random forest or some like linear models of like lassos. We're going to talk about and lasso and random forest in detail later on. And particularly for this lasso, it actually can like zero out those and wait with the like weak features. So the idea is very simple. If the feature is clearly useless for those simple models, so there's no need to include that in the later of the more complicated features. So that means we can using lassos, we can using the like random forest to actually to select those features. And this will be very, very helpful here. Okay, so we do these kind of things. We are using random forest as our and the feature selection one. So here I'm going to say select from model, but my estimator is actually this like random forest right here. We're going to still and apply this logistic regressions. I'm just using random forest as a way to select the features, right? So this is basically two different things. I'm still using the logistic regressions, but I'm only using the subset of the features. But the way to choose subset of features is I'm using the random forest to choose the subset of features. All right, so that way, this one actually give you minus 0.33. If we using wait, what's that? Okay, so this is like logistic regression here. If we using random forest to do this, it can do better, which is minus 0.3. However, this pipeline here is doing the best, which is I'm using random forest to pick the features but I'm only then I'm going to still apply the logistic regression. So basically, we are not using all 20 features. We are using only a subset of features, and that subset feature is coming from picked by the random forest. So this is very useful and a very popular way to pick the features, select from models. Okay, and also you can using like lasso if you need it. But this is not always true, because sometimes it might make performance worse. And this is one good examples. For example, if we doing this pipeline from here, so we do this wait. Random forest, logistic regressions, selections. Yeah, sometimes it will be working, sometimes it will not be working. I mean, depends on that. It just, for example, for this cases, we do the standard scalar first. We choose using random forest to choose the features. Then we do the logistic regressions. It turns out it is doing better than just doing the logistic regression or the random forest. But sometimes it's not. It's it's completely up to that. It's not always to be better. Just being said like this. Sometimes it could make the performance worse. But I'm just saying this is actually pitching out a possibility to using random forest to choose those kind of good features if you need it. Just a way, but not always the best. All right, so finally, this is the last one we can do. So this is something that is called grid search. So this is it's the most reliable one, but it's also the most computational complex. And we can do this kind of something called grid search. So what we do is we are going to train a model on a subset of features. And we're going to store those results and repeat with a different subset and compare the quality of the models and to find out the best and feature set. So this is basically like an exhaustive feature selection. So this is the most expensive one. But usually searching all these combinations will take too long, because this is like an exponential number of the combinations. So you need to try to reduce this like search space. What we do is we fix a small number n, then we iterate all possible combination of n features, and we choose the best combination. Then we iterate it through this combinations for the n plus one. So we are adding like one features at one time. That features it to be the best one and the possibles. So basically, and we need to make sure this n plus one features is, the previous best combination of features is fixed. Only one single new features is more considered, and we are going to pick that one single features that give you the best results for the possible choices. So this is called sequential feature selections. In fact, this is a one common asked questions in interviews, and to describe what is sequential feature selections, you need to know how to describe that. And of course, you can like reverse this process. That means you can start with whole complete feature spaces and to remove the features one by one until it doesn't like impair the qualities of the models. Here we are, and this things is called sequential feature selectors. So we can do this kind of ways. So we can stick with the logistic regressions. We can work with, and the same thing is negative log loss. And we are going to pick the top 3 features for that. I'm going to instead of we using forward, we're doing the reverse way. So basically we start with whole complete feature space and remove features one by one until, the quality, doesn't like impair now. So this is kind of way that we're going to do. So right here, we are looking for 3 features. This is took a little bit time. Actually, at the end for these 3 features, and we're going to remove this feature one by one until we have the best 3 features. With that, this best 3 features, the score that we get is minus 0.225, which is really good, right? So consider what we have for that. We have like logistic regressions plus, and a selection we're getting minus 0.242. And this one right here is actually give me minus of 0.235. So the best way is actually this and the sequential feature selections. Of course, the problem for and sequential feature selection, it will be really expensive. So that's why this one takes 6 seconds, which is the most time consuming one. On the other hand, this one and this one takes almost and less than 1 second. So, but in terms of result with this pipeline, did like reasonably good for both of that. But of course, if you really want to get the best feature selected, you can do this kind of and the methods. Of course, if you have very powerful computers, all your features and the number of feature or number of data is not that many, that this method could be good enough. All right, so I think that's everything I want to talk about today. I think this set of the notebook is very important. I will suggest you to go back home and to read this through and to understand these materials by yourself. Many of concepts that we present here are all frequent asked questions during interview, particularly these stuff. How do you process this data? How do you transform this data? How you do this kind of feature engineering? How do you handle with the text data? How do you handle those like missing data? And how do you select the features? All these kind of materials. These are all frequent asked questions during interviews. Not only you need to know that with your homework and projects, it's also something knowledge that you need to master during the day-to-day basis as a data scientist jobs. All right, so that's all for today.